Okay, so the other kind of problem you can be asked is to calculate hydroxide concentration or pH using a Kb value. Now, unfortunately, the data booklet doesn't directly give you Kb values, so first we're going to have to figure out how to determine them. Okay, check this out. That's the expression for Ka. Okay, so the ionization of a weak acid HX, we've used that before. And then we just saw Kb in the previous video, looked like that. Now watch what happens when you multiply them together. So these are all total general formulas. So nothing specific, it's going to be applicable to all acids and bases. If you multiply Ka and Kb of a conjugate pair, right? So HX is a general acid, X minus would be that conjugate base, right? So they match up like that. Check it out, we got HX's that cancel off. We got X minuses that cancel off. And we're just left with hydronium times hydroxide concentration. Do you guys recognize that? This is cool. Ka times Kb. This product was Kw, which is just a number, 1 times 10 to the negative 14. This is important. This is how we're going to be able to find Kb. So just the key point here is that Ka times Kb equals this number, Kw, for any conjugate pair. Okay, so now let's see how to actually find Kb. I've set up an example. We're just going to determine Kb of some weak bases here. Okay, so we use our data booklet. The first one we're doing is SO3 here, sulfite. Okay, lots of stuff to look at. Right now, you want to look in the base section. We're looking for SO3. Right here. So check it out. This is Ka of the conjugate acid, right? So Ka times Kb of this guy has to equal Kw, 1 times 10 to the negative 14. Okay, so I'm going to write this out probably only once, and then we'll just remember how to do it. So Kb is Kw, 1 times 10 to the negative 14, divided by Ka of the conjugate acid. Okay, this looks terrible, but it's effective. I even drew a line through the 14 to make it look even more terrible, but I hope it works for you. Okay, so if we're finding Kb of SO3, I'll bring this back. There it is. There's Ka of the conjugate acid. So we just have to do 1 times 10 to the negative 14 divided by this. So I lost it right here. 6.3 times 10 to the negative 8. Beautiful. 1.59 times 10 to the negative 7. Okay, I got a couple more. Part B is the same. Part C I put a star beside because there's something that can go wrong, and I'm going to help you with that. So Kb equals 1.0 times 10 to the negative 14 divided by Ka of the conjugate. Maybe I'll just write it like this, Ka conj. Be a little more formal here and actually write it down this time. So we are looking for fluoride. So we just got to divide by this, 6.3 times 10 to the negative 4. Okay, so there's Kb for fluoride. No big deal. Now let's talk about this hydrogen carbonate atom. Nothing's different, but I see so many mistakes when you're finding Kb of something that's amphiprotic. Remember, you're dividing by Ka of the conjugate acid. All right? The conjugate acid of this would be H2CO3. But you don't need to know that. You don't need to worry about that because the method is identical to the other ones. Here's the deal. What messes people up is that HCO3 is in two places. Let's try to find them. Here it is, and here it is. Oops. Okay. Well, if you follow the same procedure as the other examples, you'll use this one, the one in the base column. And that's what you do. Okay. You divide by Ka of the conjugate. If you use this one, you're finding Kb of CO3, which is not what I asked you to do. To find Kb of HCO3, just use the row where it's the base, and you can't go wrong. 4.5 times 10 to the negative 7. Okay, so I get 2.22 times 10 to the negative 8. That looks good. Next video, we're going to pull it all together.